Okay, the third method of factoring is what we're going to use when we see something that we call a difference of squares. And if you will remember when I taught you how to do the multiplication of binomials, and you did multiplication of a x minus 2 times an x minus plus 2, and what did that give you? It gave you a binomial. Why? Because x times x is x squared, x times 2 is a plus 2x, negative 2x times x is a negative 2x, and a negative 2 times 2 is a minus 4. But notice, 2x minus 2x, those two terms equal 0, and you're left with x squared minus 4. This is called a difference of squares because x squared is x times x, and 4 is a 2 times a 2. These are perfect squares. So whenever we see a difference, a minus sign between two perfect squares, we have what is called a difference of squares. And so the rule says very simply, if you have a difference of squares, this is equal to x plus y times x minus y. Or you could have negative x squared plus y squared, and this is going to equal, change the order, y squared minus x squared, which is then equal to y minus x times y plus x. So it can be written in two different ways, okay? That's your difference of squares. Now let's look at some examples in your difference of squares. How about this one? X squared minus 9. X squared is x times x. 9 is 3 times 3. So here's what it is. X times x, 3 times 3, with a plus and a minus. Some people say square root the first, write it down. Square root the second number, write it down, and plus and minus. Okay, so let's look at another one. And then of course you can check it. X times x is x squared. X times negative 3 is minus 3x. 3 times x is plus 3x. And 3 times negative 3 is negative 9. This is 0, leaving you with x squared minus 9. Exactly what we started with. And that's what you want, is to end up where you started when you check it. Okay, let's look at another problem. (25x squared minus 4). Okay, again, 25x squared is 5x times 5x. 4 is 2 times 2. Again, perfect squares with a minus in the middle. So, our two binomials, and you're going to have 5x and a 5x in the first position, a 2 and a 2, and a plus and a minus, and it is all factored. These difference of squares are the easiest ones of all to factor, I think. So, let's look at another one. 18a squared minus 98b squared. Okay? Now, on this one, what are we going to do first? First of all, you are going to pull out a greatest common factor. 18 and 98, you will find, have a common factor of 2. They're both even, So this is 2 times 9, and this is 2 times 49. So we're going to pull first of all that factor of 2 out, giving us 2 times 9a squared minus 49b squared. You see how we've combined two different factoring methods here to be able to do this one. And I will recommend later when I go through the strategy of factoring, in every method, always check for your greatest common factor first. So now this is a perfect square, 3a times 3a, and 49b squared is 7b times 7b. 7 times 7 is 49, b times b is b squared, 3 times 3 is 9, a times a is a squared. So we have the perfect squares, but to get to them we had to pull out our greatest common factor. So now let's keep factoring. Bring your 2 down, you can't drop it off, and we'll have 2 binomials now. 3a goes in the first slot of each binomial, 7b in the second number slot of each binomial, a plus and a minus, and it is all factored. Okay, let's look at one more. (16) minus an x plus 3y squared. So what's going on here? This is a perfect square because the quantity is squared. So this is x plus 3y times x plus 3y. That's a perfect square. 16 is 4 times 4. So what's going to happen? Your first factor and your second factor. 4 plus x plus 3y, and then 4 minus x plus 3y. And notice I keep this in parentheses because of this minus here. This one will simplify to simply 4 plus x plus 3y. This one is going to simplify to 4, simplify to 4 minus x, and then minus 3y. Because I have to distribute that minus to both things inside the parentheses. And this is the factoring of this expression right here. So you can see we can get pretty complex with these difference of squares, but they're not impossible to work with. Okay, you might be wondering, well, what about a sum of squares? Well, we have something we say about the sum of squares. A sum of squares, we say it is prime. In other words, it is not factorable. But this is usually the word we use for it. It's prime. So let's look at why it is prime. If I have x squared plus 9, what's happening here? Well, this is x times x. This is 3 times 3. But this plus says they're going to have to be the same sign because a negative times a negative is a positive, and a positive times a positive is a positive. So we only have 2 possible ways to check for this factoring. Either x plus 3 times x plus 3, or x minus 3 times x minus 3. But what happens when we check those answers to see, is it possible? Well, x times x is x squared. X times 3 is plus 3x. 3 times x is plus another 3x. And 3 times 3 is plus 9. Combine our like terms in the middle and we have x squared plus 6x plus 9. is this the same thing that we started with? Well, no, it isn't, is it? Because this has a middle term here, plus 6x, which does not exist in this first two-term polynomial. Therefore, this is not the factorization of x squared plus 9. And if we try this other one, what's going to happen? Again, let's check it. X times x is x squared. X times negative 3 is a negative 3x. Negative 3 times x is a negative 3x. And negative 3 times negative 3 is a plus 9. Again, combine your like terms, x squared minus 6x plus 9. Again, what is our problem? We have a negative 6x in a middle term that does not exist in the original two-term binomial. Therefore, this also is not the factorization of this particular binomial. There's no other possibility. Therefore, this x squared plus 9, which is a sum of squares, is prime. And prime is the correct term for it.